Let's wait for a few minutes. We will start after some time. Let some other students join. Can you hear me clearly? Okay. And the screen is visible also clearly. So let's start today's session. I think So, hello everyone, a very good evening to all. I once again welcome you to the introduction session related to the course Experimental Physics 1, which is being flowed this July 2023 session by NPTEL. Myself, Vivekananda Naik. I am a Prime Minister Research Fellowship PhD scholar in the Department of Energy Science and Engineering, IIT Delhi. So, let's start with today's session. Basically, in this session, we will discuss about error analysis, because in past week we had covered related to the calibration and then data plotting, etc. So at last I said that when you don't do calibration or the calibration not proper, then due to some calibration there are different errors. So measurements, there are, since the measurement can't be done with absolute accuracy, there is always some uncertainty in the measurement, and that uncertainty associated with a measurement is called as error. So when we are doing a measurement, so measurement will be having some best estimated value, and then there will be some uncertainty. So this uncertainty results in some error in the measurement. For example, if you are using a meter scale, and this meter scale has least count of 0.1 centimeter. So when you measure something, then suppose you measure the length of an object and you can identify clearly that the best estimate is 2.3 centimeter. But since you can't, so this is 2.3 centimeter, it is best estimate, then there will be some error, because we can't only measure up to this 0.1 centimeter. But for more precision measurement, we need different other devices with certain least count. So we can say this is 2.3, and since the least count of this device is 0.1, so we can say this 2.3 plus minus 0.1 centimeter. So this is the accurate value, and there are some uncertainty lies which is which is given in terms of plus or minus sign. So when you talk about error or uncertainty, then some then there are two words, two concepts which are related to those errors and uncertainty. So these are called as accuracy and precision. So this is, one is accuracy and another is precision. So we can consider an example. Suppose you have a gold ring. Suppose you have a gold ring and you want to sell that gold ring to someone you know, and you have a good relation with that person. Suppose you want to sell this gold ring to a friend and you don't want to spoil your friendship, so you want to sell to your friend with correct value of that gold ring. So you need to measure the weight of the gold ring. Suppose to your hand, it looks like the gold ring will, the weight of the gold ring will lie between 10 to 20 grams, suppose. But you are not sure about the weight of the gold ring. So you used suppose there is a gold ring. Suppose this is a gold ring, and and to your hand, it feels the weight of the gold ring is 10 to 20 gram. But you can't say, but this is not very much certain measurement, because 10 to 20 it is varying almost double. So you need some reliable source. Suppose you used a electronic balance. So you use an electronic balance to measure, and that electronic balance, suppose it has least count of 0.01 gram. So, and the result it showed is suppose 17.43 gram. So you found out that the 17.43 gram is the weight of that ring. So what we can write, the weight of that ring, del W, we can say it is 17.43 plus minus 0.01 gram. So this is the best estimate value. This is best estimate, and this is the uncertainty, because the least count is 0.001. So only 0.0 there will be. So if the least count is if the least count is smaller and smaller, then your error in measurement or uncertainty in measurement will be definitely smaller, because if this is a scale and it has the distance between two division is 1 millimeter, then suppose the object end lies here, so you will be confused with these two readings, whether it is 2 or 3. So the object, suppose this length of the object will be 0.2 to 0.3. So there is a uncertainty of 0.1 mm. But if there is a scale and it has three divisions, so it is 2, it is 2.5, and it is 3. Then it lies between 2 and 2.5. Then you can say it is 0.2. Suppose it is, and we can write it is 0.2 plus or minus. It is 0.1, but we will write it 0.05. So because since the least count here is 0.05 millimeter, so the uncertainty is reduced. So if you use, suppose now let's talk about actual thing we are talking. So it is 17.43 gram. Now as you can see, since the electronic balance is very uh, uh, sensitive to the measurement, and it has very small least count, like that is 0.01 gram. So it is giving us a particular result, but you don't know whether this 17.43 gram is true value or not, because we don't know exactly what is the value of the ring. So we can't only believe or rely on the single result. So we did the experiment. Suppose we measure the weight of the ring several times. So in one case it was from 17.44, then 17.43, then 17.45, like that. So when you make it average, then you can say that the average will be around, suppose one is 17.46, then it is 46, 45, 43, 44. So if you take the average, then the average will be how much? So there will be some average 17.4 by all the readings divided by 4. So you will be getting average. And since you see the result varying between 4.3 to 4.6, so we can say that there is some average value plus minus 0.03 gram, because the reading is varying from 17.43 to 17.46. So this 0.03 gram. So accuracy is the closeness of a agreement between a measured value and a true or accepted value. So here we can't identify whether the measurement is accurate or not, because in order to have an accurate measurement, we need to know the actual weight of the ring. So always when you talk about accurate thing or accuracy, so accuracy is always compared with the known value or true value. Suppose we know that the weight of the ring is 17.97 gram. So if one reading is coming 17.43 gram and another reading is coming 17.90 gram, then we can say that this is more accurate and this is less accurate. So when you are talking about accuracy, we need to have some known value so that we can say this has least uncertainty in measurement. So this is more accurate. But when you talk about precise thing, then precision comes from the least count of that instrument. So precision is a measure of how well a result can be determined. Suppose this is 17.43 gram. This is one reading, but another reading using another instrument that has least count of only 0.1 gram, it gave 17.8 gram. So clearly in between these two readings, 17.8 gram and 17.43 gram, the 17.43 gram is more precise, because here the least count is 0.01 gram. But when you compare it with the true value, suppose the true value is 17.97, as I told, 17.97. So when you compare it with the true value, then 17.8, it is less precise, but it is more accurate because it is very close to 7.97 grams. So when you talk about accuracy, assume that there is a ideal value that tells us how far your answer is from that ideal or right answer. So in our example, the right answer is 17.97 suppose. So if a measurement is closer to the right value or the known value of 17.97 gram, then we will be saying that this is more accurate. But if the least count of the measuring device is small, then with that measuring device we can go up to more precision. So then there will be more precise reading. So this is the basic difference between accuracy and precision. And these accuracy and precision are mainly related to error and uncertainties. Accuracy is accuracy is related to error because if it is more accurate, then it has less error. If it is less accurate, it has more error. But in the other hand, when you talk about precision, then precision is, if it is more precise, then it is less uncertain. If it is less precise, then it is more uncertain. That is, uncertainty is more. So accuracy, we can compare accuracy with error in a measurement and precision with uncertainty in a measurement. I think it is clear to all of you. Yes. Or is there any doubt? Okay, so now I think if in case you have doubt, so we can also. So now if you see this figure, then you can clearly understand the difference between accuracy and precision. So here, as you can see, the here, since this is the center of the target is yellow. So this is, if the center target, suppose we are taking this point and this is r equal to 0. The center is r equal to 0. Suppose this point is r equal to 0. So if the arrow hits here, then the distance between these is, suppose r equal to r1. And suppose the point hits here, then it is r2. So if you compare, r1 is more accurate than r2 when you talk about accuracy. So as you can see here, since here 4 arrows are lying close to the central spot, then it is more accurate. But it is high precision. How we can say that the precision is high? Because here, if you compare between these 4 positions of that arrow, then the positions between the actual positions are very close to each other. So there is less uncertainty. So high accuracy means it is more close to the correct value, and high precision means there is less uncertainty. There is less uncertainty. So as you can see here, it is accurate as well as precise. Here it is not accurate, but it is precise. And since it is spread over the central spot, but it is all the points are around the central spot, but they are not at one place. So it is accurate but not precise. And since here the spreading is more or uncertainty is more, or we can also say the standard deviation is more, then this is not accurate either, or nor it is precise, because it is lying very far from the intended zone or central zone. So this is the basic difference between accuracy and precision. So now talking about errors. So when you perform an experiment or do a measurement, then there are different sources of error. So as you can see, this figure shows what are the sources of error. So first one is the personal error, and this comes due to the mm, wrong way of doing the experiment, or if there is something, if the person is not so much skillful, then due to the way of the performing experiment, then the error will lie in the experiment, which will lead to personal error. Then incomplete definition. If you don't know about how if you don't know exactly how the experiment should be performed, then you will be missing some information, and due to that incomplete definition, you will be having some error in your measurement. And then failure to account a factor. Suppose there are different factors which affect your measurement, and one factor you can't identify, due to which it is the result is showing different. So that is also one cause of error. Then environmental factors. Environmental factors include, suppose if you are measuring something, suppose you are measuring, take an example of what can I say? Take an example. Suppose if you perform make vacuum system or vacuum operation, generally what happens, the vacuum operation you can make is more better during summer, during winter, because the humidity is less in the atmosphere. So the environmental factors like humidity, then temperature, these factors when come into your measurement or experiment, then that result in the generation of a source of error. Then another is instrument resolution. So as you're talking about, instrument resolution means least count. So if the least count is more, then there will be more error in the measurement. So that also acts as a source of error. And also in last week we are talking about calibration. And in if the system is not actually calibrated, then the true value is not measured correctly. So due to which there will be error in your measurement. And also there is zero offset. Zero offset means all your measurement will be having some error which will be throughout your experiment, because like if you remember in the last class we are talking, this should be a calibration curve, but we are getting the calibration curve of here. So as you can see, here it is 0, but here it is not 0. So this is some error, and at each point, suppose here the value should be this, but for this graph, the value is here. So if you compare at these 2 points, or at a single, suppose this is x, this is y. So for a particular value of x, the true value is this y1, but the actual value we are getting is y2. Suppose this is 1, this is 2. So these two values are different, and this different will always lie because the two lines are parallel. This line and this line, they are parallel to each other. So this much of difference, this difference between the two lines will always be there throughout the experiment. So that will lead to a source of error. Then there is physical variation, like you are doing experiment and there is some change in your measuring direction, or there is some change in your concentration, like then there will be physical variation. Another is parallax error. Generally parallax error comes when, suppose you generally this parallax error will not be coming if you are using some digital readings. So if you are, suppose this is a analog reading, suppose this is an ammeter and it has a scale like this. So it will vary from this point, and there are different numbers. So if your eyes are on equal plane with that of this arrow, then you can see clearly the readings. But if you move your head up and down, then the arrow mark will be displacing, or it will be moving up and down. So due to which there will be some error coming in your measurement, and that will be parallax error. Then there will be drift of instrument, like there will be movement of your instrument, which will also affect the experimental results. Another is lag time and hysteresis. Generally lag time, suppose you are performing an experiment and you need to turn on the stopwatch exactly at a particular incident when when an event happens, but due to some lag time there is some error in the measurement. And also if you talk about hysteresis means like we are doing in hysteresis curve of a in case of magnetic propulsion matter. Suppose when you increase a variable x and y is increasing in this way, but when you come in opposite direction, or when you do experiment in opposite direction and you come from higher value to lower value, then this graph is not exactly matching with this one graph. It is coming like this. So if you compare, this is from higher to lower value, and this is from lower to higher value, increasing value. This is from higher to lower value. So corresponding to these two lines, there are two different values. So depending upon the direction of measurement, also there are some error which is called as hysteresis error, and also this hysteresis type of error is also present in calibration factors. So these are a few sources of error, and if you broadly divide the errors into actually fundamental types, then there are mainly 3 types of error that are composed of all these previous sources of error we discussed. Some of them lie in systematic error, some of them lie in gross error, and some of them lie in random or residual error. So The first one is gross error or illegitimate errors, and these errors originate from mistakes or blunders in measurement or computation. So these errors can be minimized, and these are in our control because this comes from mistakes or blunders which are caused by us. But there are some errors like systematic errors, which the systematic error, this is present in all data points throughout the measurement. So when I talk about calibration, the calibration is not correct. So the error will be coming out throughout the experiment. So this is the example of systematic error. And if you talk about random errors or residual errors, it occurs randomly, like at one point, like here you can say this is physical variation. So this example of so this physical variation comes under this random or residual error. So suppose at a particular time when you are taking reading, your concentration is good, you are taking the reading accurate, you are doing the experiment accurately, and you are taking a reading, or you are noting down the results. And after some time, in another phase of experiment, your concentration not so good, so there will be some errors in the measurement. So like that, it occurs randomly, and if you try to repeat the experiment, then depending upon your state of mind or concentration level, the result may be different. So that are random errors. So these errors also can be minimized. One is improving the experimental procedure. So if the errors are originating from mistakes and blunders, then you can improve your experimental procedure. Then removing personal bias, and then using proper instruments. So when you use proper instruments, then the systematic errors can also be minimized, because if you use proper instrument, these instruments will be calibrated accordingly, and since they are well calibrated, so they'll be providing you good results which are more accurate as well as more precise. So errors will be minimized. So these are different types of errors or broad classification of errors. And if you talk about the, depending upon the type of calculations, the errors are different. The first one is absolute error, and this absolute error is the difference between the individual measurement and true value. So you should keep in mind that if you want to calculate error, there you should be knowing some true value. So this true value, and the difference between this true value and individual measurement of the quantity is called absolute error. So when you don't know true value, you try to calculate true value in terms of mean of all the measurements. So because only then you can say if the mean is this, so the error, if the mean is this, then the true value should lie within that range. So if you compare, so for example, suppose you took several measurements like A1, A2, A3 up to N measurements you do, then the mean of the, suppose A1 is first value, A2 is second value, like that. So after doing experiment n times, if you try to calculate the mean value, then it will be your result or true value. It will be A mean, which will be A1 plus A2 plus A3 up to AN divided by number of experiments. So however, if you compare your each observation with that mean value, then there will be some difference. Like I was saying, we used the electronic balance to measure the weight of the ring 4 times. So there is a mean value, and if you compare this mean value, then there will be when you compare the mean value with each of the readings, then there will be some difference, or there will be some change in that value. So that we will calculate, and that values are delta A1, delta A2, delta N. So delta A1 is the fast reading, the difference between fast reading and the mean value. Then delta A2 is second reading and the mean value, like that. So these delta A's, these are called as absolute errors. Since we are calculating the mean value or the true value, we can say, and then these are values of individual measurements. So either you can see if the mean is less than this A1, then it will be positive. If the mean is greater than, it will be negative. So these errors are negative. So in order to get its absolute value, we can take the mod of delta A. So this mod we generally take, and if you add all these mods, so if you see delta A1, then delta A2, like that. So if you add all these mods and take that mean, then that is called as mean absolute error. So absolute error is the difference between the mean value and each observation value or each measurement value. And if you take the mean of all these absolute errors, then that will give you mean absolute error. And if you talk about other types of error, then one is relative error. Relative error means suppose we found this mean absolute error is delta A mean. So this is here we are performing experiments more time, so we can calculate the mean. But suppose the experiment we perform single time, so there is some error and there is a true value. So the relative error will be the amount of error divided by the exact value or true value. So the ratio of these two values will give us relative error. And if you multiply with 100 and take percentage, then that will give you percentage error. So these are three different types of errors: relative error, absolute error, and percentage error. And now talking about propagation of errors. So since errors are uncertainties, they are always added up. So if one measurement is uncertain, another measurement is uncertain, then obviously those uncertain, whether they are more uncertain or less uncertainty, whether they have more uncertainty or less uncertainty, they are being added up because in each measurements there are uncertainties. So errors are always added up. So so in your lectures also you have derived all these. You must have seen how these are derived. So if you talk about sum or difference, then this is delta q is equal to delta x plus delta y. But when you talk about product and difference, then we calculate the relative error. Delta q by q is equals to delta x by x plus delta y by y. Similarly, if you compare it with the power, like it is x to the power n means x into x n times. So if you do the same thing, add n times, that will be n into delta x by x. So this is one type of calculation, calculating the error value. And another is function of a variable. So if the measuring variable is a function of some other variable, then what we will do? We will take the variation of that particular value with respect to the variable, and then the variation in the variable itself. So let me explain you it more detailed way. So for example, suppose this we take um, suppose we take position of a system. So of the position we will take S, and this position is a function of X, Y, and Z. So when you talk about error, so since these are the variables, so it will depend on the variables are X, Y, and Z. So the parameter S will depend upon these X, Y, and Z. So when you want to calculate the error in that variable, so it will also contain the relative variation of that quantity with respect to a particular variable, and then the variable of that particular quantity. So like when we are taking absolute, it is basically equal to the formula of partial derivative. So it will be delta S by del X into del X plus delta S by del Y into del Y plus delta S by del Z into delta Z. So this is the change in each coordinate or each variable or on which the function is dependent, and this is the change in that function with respect to each variable. So there will be all these factors. So when the when you have a when you have a quantity which is function of a few variables, then all these variables will play a significant role in calculating the variation or error. So these are about few principles, and now we will do a few problems. So I hope you can relate with these problems. And since we are talking about errors or different types of errors from a past few minutes, so we will be trying to solve these questions. Then the question is, in an experiment to measure the time period of a simple pendulum, the time period was found to be 2.54 second, 2.67 second, 2.72 second, 2.63 second, and 2.60 seconds respectively. Determine percentage error. So these are 5 values that were measured by an observer, and you want to find the percentage error in this observation. So it is quite easy. So I will give you a few minutes to try. So please try and tell me what will be the correct answer.
Hello, sir.
Yes, tell me.
Uh,
Sorry, I can't hear you clearly.
sir, answer is 2%.
The answer is 2%. Okay.
2%.
So any other student? So now it's the question is very simple, like we discussed in our. So like we had discussed here, these are different readings. These are A1, A2, A3, AN. So in this question, we have 6 readings. So we will calculate first the mean value, and then we will calculate absolute error for each measurement, and then there will be mean absolute error, and then there will be relative error, and then there will be percentage error, which is the answer of that question. And from so if you calculate the mean of these 6 readings, so suppose this is the time, so T mean will be how much? T mean will be 2.54 plus 2.67 plus 2.72 plus 2.63 plus 2.60 whole divided by 5. Divided by 5, which is coming out to be how much? Which is coming out to be 2.632. So should we to consider this value 2.632 or not? If the mean value is coming, because when you calculate, there will be more decimal numbers because these are not divisible by 5 up to the second decimal number. So we will be having 2.632. But if you see these readings are 2.54, 2.67. So you can clearly say, you can clearly see here the readings we are getting have the significance of up to 2 digits after decimal point. So the least count of the clock which is used to measure the time period is 0.01 second, is not it? So we will only take here 2.63 because this 2 is less than 5. So we will take only 0.6, only 2.63. So this 2.63 is the mean time. This is T mean. So if you calculate the absolute error, then T1 will be 2.63 minus 2.54. Then it will be how much? It will be 0.09. Then like that, if you calculate del T2, it will be 2.63 minus 2.67. It will be 0.04. Like that, you will get these 5 values. So if you add these 5 values, then it will give you delta T mean. Then this delta T mean will be 0.09 plus 0.04 plus again 0.09 plus since 0.60, so it will be 0. Then the fifth reading is 2.60, so it will be 0.03 divided by 5 number of readings. So it will give us 0.05. So this is delta T mean and this is T mean. So these are mean values and these are mean value of the errors. So if you take these two values, so the time T will be mean value is 2.63 and the error is 2.63 plus minus 0.05. So this is the notation of that experiment. And the question is how to calculate the percentage error. So now when you calculate the percentage error, first you need to calculate the relative error. So the relative error will be this relative error will be how much? It will be delta T mean by T mean. So it will be 0.05 divided by 2.63. So it will be 0.019. So nearly equal to up to 2 decimal point 0.02. So when you multiply 100 with it, it will be 2%. So 2% is the correct answer. So the percentage error involved in this measurement is 2% because if you compare this mean value of 2.63 to the value of uncertainty in the measurement process, then this 0.05 is 2% of 2.63. So in a measurement of 2.63, we are getting a variation of 0.05. So the percentage variation is 2%. So the percentage error is also 2%. So the correct answer is 2% here. So this is the correct answer. So now let's talk about next question. Now this question is two resistances R1 which are not denoted in terms of their exact value and then uncertainty. So if you remember, how do you if I give you a register, then how we will find out this plus minus 3 or plus minus 4 written here? Can anyone tell me how these values plus minus 3 and plus minus 4, and basically what are they called? This plus minus 3 or plus minus 4. If you talk about when I'm talking about register, then what are these values called? Anyone? We had discussed these things in the previous week. Can anyone tell me?
The mean absolute error.
No. If you talk about register, how we if you remember, I am giving you a hint. There are color codes or bands on a register. If you remember, so
Tolerance.
yes, so these are tolerance. So the resistance of the register is 100 ohm and the resistance will vary plus minus 3. So these plus minus 3 or plus minus 4 is some percentage of that value. So here, as you can see here, the if you see 100 to this 3, then it is up 3.3% or something. So the tolerance is 3.3%, and here if you see 204 divided by 200, so it will be 2 by 100. So here the tolerance is 2%. So from that tolerance, from that color of the wire or the fourth band or fifth band, we can calculate what will be the variation in its resistance. So these are denoted as 100 plus minus 3 ohm and 200 plus minus 4 ohm. So these are two resistances R1 and R2, and they are connected in series. Then what will be their equivalent resistance? So it is so please try to do this. It will be bit easier definitely. So what will be the error and what will be the actual value? We need to calculate these two value, and then like here the base here the mean value or accurate exact value can be determined. So here one is 100 value is the true value and this is its variation. So also the after you connect it in series, then the combination will also act as a register and it will be having some true values and it will be having some variation. So the answers are denoted in, or answers are represented in these ways. So tell me what will be the answer. Can anyone tell me? It is quite easy. So you can directly
300 plus minus 7.
Yes, it will be 300 plus minus 7, because if you see here, for since they are connected in series and we know if two resistances are connected in series, then its equivalent resistance is how much? R1 plus R2. So since it is R1 plus R2 and we are discussed, if you see this formula, when these two quantities are added, then the errors are or the uncertainties are directly added. So there will be no relative error or other things. There will be simply addition of those uncertainties. So when you do, it will be R equivalent will be R1 is 100 plus minus 3 plus 200 plus minus 4. So these two values 100 plus 200 will give you 300, and then these two uncertainties 3 and 4 will give you 7. So this is 300 plus minus 7 and ohm. So the equivalent resistance will be 300 plus minus 7 ohm. Now coming to the next question. The question is, the resistance of a conductor is given by R equals to V divided by I, or simply ohm law, V is equals to IR, where voltage is 200 plus minus 5 volt and current is 200 plus minus 0.4 ampere. Then calculate the percentage of error in R. So this is a bit different of that. This is a bit different question when you compare it to the previous question that was being directly added, but here we have to do some extra operations. So try to do this and tell me. I'll be giving you 2-3 minutes, and then we will discuss. So I also encourage everyone to solve and then tell me answer. So it will be good. If you are trying to solve these questions, it will definitely help you in your assignment, solving assignment questions. Also, it will be better for your practice. And also, if you are appearing for the exam, then these types of questions you can also face in your exams of this course. Yes, what will be the correct answer?
First one.
Once again,
The first one. 2.5 percentage.
2.5. I don't think. Let's solve it. So as you can see here, since it is a case of division, so we will take the relative errors or percentage errors. So for each voltage and current, we need to calculate the percentage errors. So when you calculate, then this, since R equals to V by I, then this delta R by R will be how much?
The screen is not displaying.
Okay, sorry. I think there are some. So can you see?
Yes, sir.
Okay, thank you. Thank you for saying, because I also can't see exactly is my screen is being shared continuously or not. Now I can see. So when you talk about this relative error, then it will be delta R by R equal to delta V by V plus delta I by I. So the percentage of error will be delta R by R into 100, which will be equal to delta V by V into 100 plus delta I by I into 100. Or we can first calculate this value and then we will directly calculate this. So delta R by R will be how much? So when you see here, this is V, this is delta V, this is I, and this is delta I. So it will be 5 divided by 200 plus 0.4 divided by 200. I think 1 minute. It's not 200, it is 20. So the answer is calculated using this 20, not is 200. It is 20 only because so please correct it. It is 20. So 20 plus minus 0.4. So it will be so it will be 20. So when you calculate, it will be 5 by 200 means how much? It will be 1 by 40 plus 0.8 by 40. It will be 1.8 by 40. So delta R by R will be into 100. It will be 1.8 into 100 by 40. It will be how much? It will be 180 divided by 40. It will be how much? 4.5%. Is not it? So the correct answer is 4.5%. Is the correct answer. So since here the relation, like in previous case, it was R1 plus R2. So we are direct adding the values. But here we can't add or we can divide these values. We will take the relative errors in this case. And according to the formula, when there is a product or division, these relative errors are added up. So it will be delta R by R equals to delta V by V plus delta I by I. So taking the percentage, it will be 4.5%. So is it clear to all of you or is there any doubt? Hello? Is there any doubt?
No, sir.
Okay, so we'll proceed to our next question, our fourth question. Now here, the question says the capacitor of the capacitance C equals to 2.0 plus minus 0.1 microfarad is charged to a voltage of V equal to 20 plus minus 0.2 voltage. What is the charge on the capacitor? So here we have C, we have V, and we need to find out Q. So can anyone tell me what is the relation between these three quantities? Yes. Yes, can anyone tell me what is the relation between these three quantities?
So Q equal to CV.
Yes, so this Q will be equals to C into V. So this is a product of these two variables, capacitance and voltage. So these are given C plus delta C and V plus delta V. So this C is 2.0 and this is 0.1. But these are microfarad. If you see, these units are different, so you need to keep this in mind. This is microfarad, and then this V is 20, and then del V 0.2. So these are the values. So similarly, since it is a product also, so we will directly put delta Q by Q, because here if you found delta Q by Q, then we will found how to represent these quantities. So we will use the formula for division and we will be calculating. So try to calculate what will be the values. Tell me what will be the correct answer.
The option B is correct.
Okay, so any other student who have done this? You can also tell me what what will be your answer. Yes, any other student who have calculated? So let's solve. So since Q equals to CV, so the best estimated value we can directly calculate. It will be 20 into 2 because this C is 22 and this B is 20. So this Q will be C into V directly 2.0 into 20, which will be 40. If it is microfarad, so it will be 40 into 10 to the power minus 6 coulomb. So this is Q. Now how we will calculate delta Q? Now the relation for the formula for delta Q calculation is delta Q by Q is delta C by C plus delta V by V. So this is the formula. So when you put the values 0.1 by 2 plus, I request everyone to mute themselves. It will be how much? It will be 0.1 by 2 plus 0.2 by 2. Will be 0.1 by 2 plus 0.2 by 20. So 0.1 by 2 plus 20 will be how much? If you solve it, 0.05 plus 0.01 will be 0.06. Then delta Q will be 0.06 into Q, 0.06 into Q is 40 into 10 to the power minus 6. It will be 2.4 into 10 to the power minus 6 coulomb. So if you add, this is 2.4 into 10 to the power minus 6 coulomb. This is 14 into 10 to the power minus 6 coulomb. So the result will be Q plus delta Q. It will be 40 plus minus 2.4 into 10 to the power minus 6 coulomb charge. So this is the correct answer. Then talking about next question. Now the error in the measurement of a sphere is 2%. That would be the error in the calculation of the surface area of the sphere. So it is related to the question of if the variable function of some power. So your radius is given So since the error in measurement of radius is 2%, that will be the error in measurement of area. So can you tell me what will be the correct answer?
The 4%.
Yes, so it is very easy when you can clearly see the error in measurement R is 2%. That is delta R by R is how much? 0.02. Is not it? Then simply when you talk about area is how much? Radius of the sphere, it will be 4 pi r square, 4 pi r square. This is constant, so 4 pi. The deviation in, since it is a constant, the deviation is 0, so there is no error in there is no error involved in 4 pi, so there is only r square. So a died proportional to r square. So delta a by a will be 2 into delta r by r. So it will be 2 into delta r by r is 0.02, will be 0.04. So in terms of percentage, it will be 0.04 into 100. It will be 100%. Since here the exact value of radius we don't know, so we also can calculate the exact value of area. If the exact value of area we know, then if the exact value of radius is given, then we can calculate the exact value of area. But in this, if whether there is a value of radius given or not given, the error in area will be always twice of that error in radius. I think this is clear to all of you. Then we can proceed to the next question. Now the question says the temperatures of two bodies measured by a thermometer at T1 equals to 20 degrees Celsius plus minus 0.5 degrees Celsius and T2 equals to 50 degrees Celsius plus 0.5 degrees Celsius. So calculate the temperature difference and the error therein. So it is this question is related to the difference. Difference means T1 minus T2. So you need to subtract these two. So you need to find this the difference between these two readings because it has some uncertainties and also it has some true values or best estimated values. So what will be the temperature difference with error? So error is given in plus minus terms and the temperature difference given in first term. So tell me what will be the correct answer for this question.
The 30 plus minus 1.
Okay, any other answer from any other students? Sorry, tell me. So here, since the temperature difference will be T1 minus T2, so the temperature difference T is T1 minus T2. Again, this T1, it is T1 plus delta T1. This T2 is T2 plus delta T2. So this T1 is 20, delta T1 is 0.5, T2 is 50, delta T2 is 0.5. Then this T will be the best estimated value or true value will be T2 minus T1, 50 minus 20, 30. This is T, but the error, since the errors are always added, so it will be delta T will be delta T1 plus delta T2. It will be 0.5 plus 0.51. So the temperature difference will be 30 plus minus 1, and unity is always important. So it will be 30 plus minus 1 degree Celsius. So this A is correct answer. Here it will be, sorry, here it is. So the correct answer is over here. Correct answer is 30 plus minus 1 degree Celsius. Now, another question is the length, breadth, and height of a rectangular block of wood are measured to be 12.13 plus minus 0.02 centimeter, 8.16 plus minus 0.01 centimeter, and the height is 2.43 plus minus 0.01 centimeter. Determine volume of the cube with percentage error. So this is the question. You have length, breadth, and height. You need to find the volume. Since length, breadth, and height have their uncertainties in the measurements, they have errors. So we can calculate the error in volume also. We have formula, and you know the formula in case of product. And now tell me what will be the value of the volume of that rectangular wood block.
Sir, option C.
Sorry, once again.
Option C, sir.
Okay. Any other student? Let's solve this question. Now here you have length, breadth and height. This is L. L is 12.13 plus minus 0.02 centimeter. Breadth is 8.16 plus minus 0.01 centimeter. 2.34 plus minus 0.01 centimeter. So since the volume is L into B into H, so the best estimated value will be 12.13 into 8.16 into 2.34. So as you can see here, in previous answers, here there were no percentage, 30 plus minus 1 and both are in degree Celsius. But here, this is in centimeter cube, but this is in percent. Like same in all cases, this value is different and it is percentage only. So the error is given in percentage here. So we need to first calculate the error and then we will be dividing that error with respect to this true value and then we will be finding the percentage of error. So uh, yeah, the multiplication will be 231.62 centimeter cube. So this is the answer, but how this value comes? Then this 0.71 will come from the uncertainty. So delta V by V will found, and then this delta V by V into 100 will give us the percentage of uncertainty. So delta V by V will be delta L by L plus delta B by B plus delta H by H. So when you put these values, 0.02 by 12.13 plus 0.01 by 8.16 plus 2.34 by 0.0101, then it will give you 0. How much? It will give you 0.0071. Then in terms of percentage, it will be 0.0071 into 100%. It will give you 0.71%. So it will be, the correct answer will be this C, 2.31, 0.62, 0.7. But if I will write it in different way, then it will be 0.0071 into this V. 0.0071 V is how much? 231.62. So when you multiply these two numbers, 1.644. So it will be 231.62 plus minus 1.64 centimeter cube. But here, since this is given in percentage, so the centimeter cube is only written after this 231.62. Now, that comes to our next question of the day. This question says, a register has a marking as 470 ohm and 10%. What will be the true value of that register? Can anyone tell me? If the register is marked as 470 ohm, 10%, then what will be the true value of that register?
The 470.
No, the question says the register has a marking as 470 ohm and 10%. Then what will be the true value of register means? What are those two values? Within which the value of the register will vary, but there will be more since the tolerance is 10%, so the resistance value will vary between the two numbers. So what are those two resistance values? So if you see here, here it is given, it is 470 and 10%. Like here it was given 231.62 plus 0.71%. So the value is varying between the 0.71% of this 2.31, which is 1.64. So it will be 2.31 plus minus 1.64. So it will be, then since it's 10%, we can write it 470 plus minus 47 ohm. Then the resistance will vary from 470 minus 47 to 470 plus 47. So the values will be 423 to 517 ohm. So these will be the values of that resistor. So the value of the resistor will vary between 423 ohm to 517 ohm. So this is the question. Now this question says the refractive index of water is found to have values 1.29, 1.33, 1.34, 1.35, and 1.32. There are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 values. Calculate the mean value, absolute error, the relative error, and percentage error. Mean value, absolute error, relative error, and percentage error. So calculate it. Calculate it. I will be to calculate all these values of mean value, absolute mean error, mean value of that quantity, absolute error, relative error, and percentage error. I'll be back in a few minutes. Yes, anybody calculated? So when you ask what is
Hello,
mean
sir.
value, yes, tell me.
The mean value is 1.33.
Yes, then
Mean absolute value is 0.02,
yes,
and relative error is 0.02, and percentage error is 2%.
okay. So here let's calculate now. The mean value is quite easy. If you will add all these numbers and then we will divide by 8. So it will give, as you said, 1.33. Then from this 1.33, like we did in the first question of the day regarding to time, so we will subtract each and then there will be del mu. These del mu's are absolute errors. So it will be 1.33 minus 1.29, 0.04. Then since the second reading is 1.33 also, so there will be no absolute error. Del mu 2, del mu 1 like this. And after calculating all these del mu's, then the mean absolute error will be the summation of all those mu's divided by 8. So the summation will be 0.14 divided by 8, which is 0.02. So this 0.02 is your mean absolute error. Then the relative error is uh, the relative error is absolute error divided by mean value. The absolute error is 0.02 divided by mean value is 1.33. So it is 0.015, which can be, since it is the numbers is 3 points, 3 digits after decimal point, but all the readings are in 1.29. So the 2 digits, so the number is, so the here you can approximate it to 0.02. So 0.02 will be the relative error. But when you calculate percentage, then we can multiply 100 with this number because it will give us 1.5. And here 1.5, there are 1 point. So since this will give us 1.5 and 1.5 lies with has significance because here after decimal there are 2 points, but here there is only 1 point. So this 1.5% will be the percentage error. However, for calculating the relative error, it is approximated to 0.02. Okay. Then next question. The question says a current of 3.5 plus minus 0.5 ampere flows through metallic conductor and a potential difference of 21 plus minus 1 volt is applied. Find the resistance of the wire. Very similar type of problem we have solved today. You just need to do the calculations. You all know how to solve it. So can you solve it quickly and tell me what will be the resistance of the wire? Yes, anyone? Since we have solved this type of question earlier, so simply we know R equals to V by I. So delta R by R will be del V by V plus del I by I. Here del V is 1, V is 21 plus delta I is 0.5 and it is 3.5. It will give us 0.191. So we can write it 0.19 approximately. Then when you calculate the actual resistance, it will be 21 by 3.5. It will be 6. Delta R by R will be, so this is delta R by R. Then delta R will be 6 into 0.19. It will be 1.14. So the actual resistance of the wire will be 6 plus minus 1.14 ohm. This is the correct answer. Then rectangular board is measured with a scale having accuracy of 0.2 centimeter. So this is 0.2 centimeter. The length and breadth are measured as 35.4 centimeter and 18.4 centimeter respectively. Find the relative error and percentage error of the area calculated. So this is very similar, but there is some trick, a bit of trick here. All are very similar numbers. You just need to do the calculations. So please try to do this question and tell me what will be the relative error and percentage error of the calculated area. So when you calculate it, here since here we want to calculate the error, but we don't know the error in measurement of these values. But here, as you can see, it is clear that it is written here the scale having accuracy of 0.2 centimeter. So for both the calculations, for both the calculation, like if L is L plus delta L, it will be 35.4 plus 0.2 centimeter, and width is W plus delta W. It will be 18.4 plus 0.2 centimeter. So this 0.2 will be a error in all these L and W because the scale has accuracy of 0.2 centimeter. So the minimum uncertainty is 0.2 here. So similarly, if you calculate, area will be L into W. It will be 35.4 into 18.4, which gives clearly 651.36 centimeter square. Now talking about delta A, it will be delta W by W plus delta L by L, which will give you 0.017 or 1.7%. So the relative error is 0.017. This is the relative delta A by A relative error, and the percentage error is this is percentage error. Now the next question is the physical quantity x is given by x equals to a square b square divided by c into root d. If the percentage errors in measurements in A, B, C, and D are 4%, 2%, 3%, and 1% respectively, then calculate the percentage error in the calculation of x. So it involves powers of some variables. So directly we will be using the formula like, so x is a function of A, B, C, and D, is not it? So delta x by x into 100 we need to calculate, and we are given with delta A by A into 100, which is 4%. Like that, for B it is 2%, for C it is 3%, for D it is 1%. So you can simply calculate. So use the formula when there is powers of some variables involved, and you can simply calculate what will be the percentage of error in calculation of x. So here, since in both multiplication and division they are added and they have powers here, so it delta x by x, when you talk about percentage, it will be 2 into delta A by A plus 2 into delta B by B plus 1 into delta C by C plus half into delta D by D. Since all are percentages are given here, so it will be 2 into 4 plus 2 into 2 plus 3 into 1 plus 1 by 2 into 1. It will give you 8 plus 4 plus 3 plus 0.5. It will be 17.5%. So the percentage error in calculation of x is 17.5%. Similarly, now So the last question of today's session. This says what roughly is the percentage of uncertainty in the volume of a spherical beach ball whose radius is r equals to 0.84 plus minus 0.4 meter. So here radius is given 0.84 plus minus 0.04 meter. We need to find out volume which is proportional to RQ. So delta V by B will be 3 into delta R by R. So put those values and tell me what will be the rough, since it is roughly, so you can from the option you can choose the answer closest to a particular option. So tell me what will be the correct option for this question.
The 15%.
Sorry, once more.
15%.
Yes, it's 15%. How we calculated? Because here delta R by R, delta R you know, delta R will be 0.04, R is 0.84. Simply, it will be 0.047. So 3 into 0.047, it will be 0.141. When you convert to percentage, it will be 14%. So roughly we can say we can take it roughly as 0.05. So it will be 15%. So 15% is the correct answer. So now we have discussed about the error analysis part. Now after in the next week, we will be talking about the experiments covered in that week or particular week, and we will try to solve numericals depending upon these concepts are the principles with which the experiments are formed and the values are calculated. So these are some basic things which you need to keep in mind while performing experiments. We started with measuring devices like meter scale. We calculated least count of meter scale, then vernier caliper, screw gauge. Then we then we studied about a lot about voltmeter, ammeter. Since all these are made up of galvanometer, then first we covered galvanometer, and then we studied how this galvanometer is converted into ammeter and converted into voltmeter. Then we studied about different electrical components like resistors, inductors, capacitors, and then cathode ray oscilloscope, which has a cathode ray tube and beam of electron, the source of a electron beam, which provides through which we can see the waveform or the signal in the photographic plate or fluorescence screen. And then today we discuss, then in the previous week we discussed about different techniques like data plotting, data measurements, calibration, and today we discussed about error analysis. So all these basic analysis are covered now. In the next week we will be discussing about the experiments. So is there any doubt regarding to the today's session?
Yes, sir, I have one doubt.
Yes, tell me.
Sir, what will be the percentage error if the two resistors are connected in parallel?
If the two resistors are connected in
Parallel.
Okay, so we can.
Sir, I have a question.
Yes, tell me.
Sir, if R1 equal to 6 plus minus 0.3 kilo ohms.
6 plus minus 0.3
kilo ohms.
then
and R2 equal to 10 plus minus 0.2 kilo ohms.
2 equals to 10 plus minus
0.2 kilo ohms.
0.2 kilo ohms. Yes, then that will be the.
So the are connected in parallel combination.
Sorry, once again, I couldn't hear you properly.
Sir, what will be the percentage error if they are connected in parallel combination?
So now this is R equal will be R1 R2 divided by R1 plus R2. So these are two quantities. Now these two quantities are, one is product and one is addition. So for this we will simply do delta R1 plus delta R2. We will calculate R1 plus R2, and for R1 R2 we will do, suppose this is one quantity, we can consider now this is R equivalent is R1 R2 divided by R1 plus R2. So this we can consider one quantity. Suppose this is Q and R1 plus R2, this is P. So R equivalent is P by Q. Then the delta R equivalent by R equivalent will be delta P by P plus delta Q by Q. Then again we will find delta P and delta Q. But here in delta P, what will happen? In delta P by P, we will simply calculate, since here the term is R1 into R2, so it will be R1 delta R1 by R plus delta R2 by R2. So from this we can calculate delta P by P, and for delta Q by Q, we simply will be delta Q is equal to delta R1 plus delta R2, and by Q will be R1 plus R2. So through this method we can calculate. Then after calculating these two values, we will add here, and when you put it, you will find this R equivalent and its error. Is it okay with you?
Okay, sir.
Yes. Any other doubts? Basically, you have to see like what we did in the discussion. We said propagation of error, how the error is being introduced in the system. So since it depends upon two quantities, so in both the cases, the nature of propagation of error is different. In one case, they are being added, and in other case, they are being multiplied. So since they both have different types of propagation, so we'll calculate error for both of them, and then we will use the formula for division and we'll calculate. I think we should stop here, and we will discuss in the next session regarding to the experiment that we have performed, that we will be studying in these weeks. So thank you all. Good night.